Hi guys, can I get a sound check?
Hello, Professor.
Hi, thanks.
Hi, Professor. How are you?
Good, thanks. Why is it? Oh, I know. Hold on a second, guys. Sorry, turn Bluetooth. I'm still connected to the. Okay, can you guys speak again, Sriman?
Hello?
Hello.
Okay, great. That's great. Thanks. I was still hooked up to my speakers next door. Hmm. What happened to all you guys? You decided to turn off your videos? At least last week, a few people had their videos on. Hey, thanks, Ian.
No problem, no problem.
Get some support. All right. Are you local, Ian?
Yeah, I'm like 20 minutes from campus, so.
Oh, cool.
Yeah, I'm local.
Nice.
Shoot.
Trying to figure out is.
Can you see me, Professor? My bad.
Yeah. See you. Thanks, Raymond.
No problem.
How do I do this? Sorry, guys, that was me. Oh, good. Good. Okay, guys. Can I get one more sound check? It's because I don't trust myself.
Hello.
Okay,
Hear
awesome.
you.
Testing. Okay, guys. So in 5 minutes, so at 5:35, quiz 0 is going to show up on Blackboard. So it'll be under, I think there's like a section called tests or something. So you can download the PDF and work on it. The reason I made it 5:35 is because I wanted to spend a little time to talk to you guys about the instructions for submitting quizzes. We're going to have several quizzes, 4 or 5, hopefully more, maybe, I don't know, as many as we'll get a chance to do, just to give you guys lots of opportunities to like make up for issues, and you're not like just going to get screwed over because you screwed up a midterm or something. Also, hopefully it'll encourage you guys to stay with the plan. But I'm still angry about this from last semester. So I made these instructions because there were some really bad submissions. So I have these rules, and I just wanted to go over it with you guys. Because believe it or not, so rule 1, people would submit their quizzes without their name either on the quiz, on the paper, or on the file. And like, what do I do with that? So anyway, let me take a step back. So what happens is the quiz will have a certain number of pages. It'll be a PDF. You can either download it, print it, write on it, and then sort of scan it and send me a PDF back. You can write on it if you have like an iPad or something like that, that's fine. Or if you have none of those, you can just use your own pages and just take a snapshot out of them with your cell phone and submit it to me in a PDF format, whatever you like. So you have to email me the PDF formats at the end of the quiz. So the quizzes will be probably like 30 minutes, 25 minutes, 20 minutes, etc. Today's will be 20 minutes. Today's is not graded, but I just wanted to go over, it's just sort of a cleaning up our pipeline and making sure you guys know the rules. Okay, so put your name on the actual piece of paper that you're scanning, or if you got an iPad, put your name and date on every page, please. And also on the file that you submit, on the PDF file, okay? Make all
Professor,
yes.
sorry about that. Do we submit it on Blackboard or do we email it to you? Because you just said email it to you.
Yeah, email it to me.
Okay.
Yeah, and what I'll do is I'll have to, Gradescope is a little weird. Tests, I have to basically upload it into Gradescope, and hopefully we'll go from there, okay? Now you need to organize all your pages into one PDF file, okay? So put your name on the file. And then if you're using your own paper or PDF or whatever, you want to return exactly the same number of pages that's on the PDF, okay? So this particular quiz 0, once you get the PDF, you'll see it's 4 pages, and you're going to return 4 pages to me. Even if one of them is blank, I don't care. 3 of them are blank, I don't care. But just return 4 pages in your PDF. So these top 4 rules are, like I said, I'm very angry about last semester. So it's going to have dire consequences if you guys fail these rules. I'm just not going to grade that quiz for you. That means you'll get a 0 for that quiz. Okay. So some of the other ones are instructions that you'll lose points on, but not so severely. And so I can tell you that when I grade, okay, I'm a really big believer in partial credit. I'm a really easy grader. But to me, grading isn't really black or white unless you return something that's absolutely pristine, absolutely correct, or a blank page. Everything in between, I end up using a lot of my judgment to give you guys partial credit or full credit, depending on what you have. So make sure you follow the instructions, use the symbols we've used in the class, make sure you have units assigned, etc. So, but again, the top 4 are the major rules. Okay, guys. So the quiz should be on the Blackboard now. If you are not, some of you guys I think are still don't have access to Blackboard. David, I think I don't know if you're on, but if you don't have access to Blackboard, send me an email right now. I'm going to go on my inbox and I'm going to email you guys the PDF. Okay. Go ahead, guys. Good luck. Again, this isn't graded. You just have to do it and turn it into me. Okay, David, I just emailed it to you. So guys, you have till 5:55 to email it to me back. Okay, guys, you can go ahead and email me your PDFs. Can you guys still see my screen? I'm not sure why I'm missing my own shared screen.
The screen share, Professor?
Yeah.
No, I'm not
You don't
able.
see
No, we
it?
can only see your camera.
What's that?
No, I don't. I'm not able to see it.
No,
Screen share
let
at
me
least.
try to, sun blew up here. Okay, good. Okay, so guys, I hope everybody already emailed emailed the PDF back to me, your PDFs back to me. If you, so again, this is for you yourselves to get a feel for how you're doing with the background for the class, and also clean the pipe of, how we're going to handle these quizzes, so you don't lose points unnecessarily when we get into the actual quizzes in a couple of weeks. So if for some reason you had internet problems or whatever, keep trying, get the quiz, give it your best shot, and send it to me so that we can, again, make sure that you don't want quiz one, this was quiz zero, you don't want quiz one to be your like sort of debugging environment, because you'll actually lose points at that point. Okay, so I don't know how you guys feel about that test, that quiz. Some of you are probably feeling pretty good about it. It's just really an indication of, some of the classes, you took before this. And, some of you guys may feel like, well, you didn't do well, or, whatever. Well, like, you have the weekend to, my suggestion is to look at chapter 1 of the book, and go through it, and sort of get yourself refreshed with some of these basic concepts of circuit analysis, and etc. And let's see. Okay, so that's that for the quiz. And then I got a question from one of you guys for recommendations for a book to help you guys develop good study habits. And I suggested, this is one I just happened to read a few months ago. It says How to Win at College. This guy, Cal Newport, the reason I know about him is he's got a bunch of really good books about deep work and so on for professionals. I thought, I don't know, there's probably other books about how to do this. I think the point I wanted to make for you guys, some of you guys already have good study habits. I didn't when I started undergrad. I went to public school in California, and it was just too easy. And then I got into college, and it was too hard, and I didn't have the study habits to help me survive. So it took me till my like junior year till I started to develop my own study habits on my own, and it completely like changed my grades. At least by one, I was probably like getting mostly B's, and then I ended up with like A's and A pluses. Just same person, same level of intelligence or lack thereof, different study habits. Okay, so anyway, if you don't do this, just I wanted to tell you guys there's this material available out there. If you're spending a lot, you feel like you're spending a lot of time studying, you're not getting results, or you just don't know what to do, it's like, do yourself a favor. You're going to have at least 2-3 more years of this business, and you don't want to be struggling the whole way. So there's a few things that also, the other place to look, I think that, like I mentioned, this textbook by Razavi, I don't know how else to put it. This dude is a god of microelectronics teaching. And so he's got some really good advice for students at the beginning of the book about, your reading, problem solving, etc. So one of the important things to do for you guys, I'm going to start giving you a bunch of reading assignment, quote unquote. Okay, so nothing in the class is graded except the quizzes and the final. So the homeworks I give you, I'm also going to give you this homework solutions, reading assignments. It's up to you to do it or not. What I would suggest, and it's going to be, the reading assignment is going to be huge. Okay, so the first chapter of this thing, I don't know if you guys can read this, is don't do all of your reading. Okay, so when I give you a reading assignment, what you should be doing is skim the reading assignment, or read, if you're going to read every single word, read it like you would a novel. Don't get stuck and try to solve it. It's just, you're trying to figure out what I'm going to be talking about during a lecture. So it won't be the first time you've seen it. You have a sort of overall view about what's coming. Okay. So mostly skim the reading or read it like you would a novel. Either come to the lectures or see the recorded lectures, and then hit the homework problems. Do a lot of problems. Okay, that's just the way the circuit design works. You got to do, I think probably most of engineering works. You got to do a lot of problems, not just listen to the lectures, not just read the book. That's just half of the problem. Okay. And then when you do the problems, okay, do not, so I was watching, my wife's a athlete, I'm not, obviously. And we were watching the sports psychology series on TV, whatever, on Netflix or whatever it was. And the guy made the key point about deliberate practice, okay? So if you want to think about this class as if it was a sporting event, sort of the classes, the homework problems, reading, all that stuff is practice. And the quizzes, the final, etc., those are the games. Okay, that's where you win or lose, you get points for the season, and at the end of the season, you're at some level in the class, if you want to think about that analogy. Okay, so what you want to do is, and what the sort of the sports psychologist, the key point he was making is, not every practice is great. You want to do deliberate practice. So you want to be thinking about what you're doing. How does the problem you're solving, how does it fit? What's the point of that chapter, or what's the point of what we're trying to do? Okay, so be deliberate. So anyway, so don't do all the reading. Those are some of the stuff. Some of this stuff is, it talks about build study system. I like that. It says, but you got to take it or leave it. Chapter 14 is never nap. I love to nap. My life would just be not worth living if I don't nap. So you got to just sort of take it or leave it, because there's a lot of stuff. Don't study in groups. I think that's a great idea. When I was studying with groups, I didn't do well. It's a little bit harder to study with groups in the pandemic days, but there's like a lot of good stuff here. Chapter 73 is start fast and slow. When you got you won't have this in this class, but let's say if you have a lab that takes, or a paper due or something that takes 3 weeks to do, go at it hard at the beginning, and you can sort of just slow yourself down as you go, spend less time as you go. I went to, like I mentioned, my freshman and sophomore years in undergrad was just a disaster. I was dying. I mean, I was really, really flailing. Okay. My junior year, I studied by myself. I did a lot of problems, studied consistently we were on the quarter system, but anyway, studied consistently during the session. And I kid you not, I would not study the week before finals or finals week. Just did not need to at that point. I'm not joking. I just go in, take the final, did great. It was amazing. Like not having to cram, because everything was good. I was all, I was I hit it hard before the tests, and so test week, and I would go in a very confident way. So anyway, just a book I recommend. It's the only, like, I just happened to have read it recently, but go out there, look at it. There is such a thing as study skills, and if you guys, again, some of you guys, I just can tell by the grading. Some of you guys have great study skills. You're on top of it. You're good to go. And some of you guys are kind of struggling. So, just make sure there is a way out of this situation. Okay, so that was that. And then now let's start. So today's still a little bit of an introduction. And I wanted to, one of the things that I always had a hard time in my my undergrad was that I didn't see the overall pictures. I would take some classes and there'd be these concepts and I didn't see how they fit together. So there's a couple of important concepts here that's just not just important for this class, but important for any kind of electronics, okay? And so if you do nothing else in this class, sort of my suggestion is try to understand this. This is some really, really basic concepts, but it's just not explained well. I'm probably not going to explain it too well either, but I'll try with you guys. I'm going to explain it at sort of the level I would explain what we do to my neighbors who are very smart people, but they're like bankers and doctors and stuff, so they're not electronics people. Okay, so the first concept I wanted to talk to you guys about was the concept of signal and noise. Okay, so signal is a signal, noise we'll talk about. Noise is a general term in electronics, in engineering, really in general. So it doesn't just mean something you hear. You guys are probably familiar with the concept of signals and noise now, but it's some thing on top of the signal that's just reducing the amount of information of the signal. That's sort of what noise means. So now this is like the insult your intelligence time with my example of signal and noise. Let's say we use a sort of a personal example. So you have a friend A, okay, and then you have you, and then you have friend B, okay? So your friend A calls you at 11 a.m. on a weekday, okay, and tells you it's a big sale on iPhones. Just like using iPhones as an example. So go to website, so go to, he tells you go to www.bigsale.org and use code sale 25 to get 25% discount. And and then use code free case to get a free case. Okay, so let's say you're not, you're like me, 11 a.m. is my sort of prime alert time, so that's good. And let's say you've had your bagel and coffee. So you got a lot of good blood sugar level, you've got a lot of caffeine in your system, you're at your maximum alertness. Oh, and then your friend says, hey, pass the word on. Tell friend B about it. So, okay, so you call up friend B then, And now you're now a buffer, okay? So you're just getting in an electronic context. You're getting information from your input and you're trying to replicate exactly on your output. So you tell your friend B, hey, go to www.bigsale.org, put in sale 25 for the 25% discount, and put in free case for the free case discount. Great. Okay, so your very, very alert you is like sends the information as is. Okay, that's a situation of zero noise. So you injected zero noise into that conversation. You passed it on. Okay, now let's say your friend instead calls you at 7 a.m. Okay, you did have your bagel and coffee, but you're not a morning person. Okay, then you call up your friend B, you're not quite there. You get all the big information in there. Hey, bigsale.org. So again, check. So this is 11 a.m., 7 a.m. Okay, sale 25, but you weren't really, you weren't all there. You were kind of alert, but you forgot to mention the free case. Okay, not a big deal. I don't know, free case is, I don't know, maybe 25 bucks. So this is zero noise. And now you injected a small amount of noise. Let's call this low noise. Okay, so a small amount of the information got lost in the buffer that is you. Okay, now we can keep taking this further. So let's say it's 7 a.m. and you hadn't had your bagel, hadn't had your cup of coffee yet, and you called and told your friend, hey, it's bigsale.org. Okay, but you forgot to tell them that, or you mixed up it, instead of sale 25, you tell them it's sale is the whatever the code word, and you forgot the free case. Now you're talking about a high noise system. Okay, and let's say it's 7 a.m. you haven't had your bagel, you haven't had your coffee, and you got a hangover from the night before, and you're just like whatever, and you tell your friend B, hey, there's a sale. I heard there's a place on bigsale.com. Basically, just zero information gets passed. Okay, in that case, like now your sort of noise is equal to your signal. So that's in the context of you. The signal is the information you're trying to pass, and then noise is however that signal gets messed up. If you told, friend B, hey, it's, again, if it's sale 27 instead of sale 25, again, you've destroyed the signal. Okay, so that's the concept of signal and noise. Okay, so let's look at the same thing in a context of electronics, like what we're doing in this class. Okay, let's say you had so in electronic context. Okay, let's say you had a microphone. Okay, and then you were going to record something. Okay, so there's a microphone. This is a recorder. I apologize in advance for my handwriting, guys. Recorder. Okay. So now let's see if you were going to put an oscilloscope here to look at what's coming out of the microphone as you're speaking or playing something in there, okay? So I'm gonna draw what you'd see in your scope. So the scope is gonna give you some indication of, you'll see time in the horizontal axis and voltage in the vertical axis in your scope. And you'll see some small voltage signal coming out of your microscope, okay, with time. Okay, cool. So the problem is now that's too small. So the amplitude of this guy is too small. It just does, you can't hear it when you record it. So as I'm sure most of you guys know, what you do in, you know, almost every case is you stick a amplifier, okay, in between. And amplifiers are one of the things we're going to spend a lot of time in this class. Different types of amplifiers. They are used in almost every electronic thing that's, you know, analog. And I'll talk about analog versus digital in a minute. And so you put an amplifier in there. What does an amplifier do? It just takes the input and the output is some gain. Usually they put A as the gain of the amplifier. Maybe it's 5, maybe it's 10, maybe it's 10,000, okay, times the input. Okay, so if I was gonna put a scope probe on this one, on this point, on the output of the amplifier now, what I see, and I'm gonna try to replicate this. I'm gonna do time and then voltage. So remember, it's the output of the amplifier with the input being here. So this is your input. Okay, and this is the output of the amp. So you'll see something like, I'm going to try to replicate that, but it's hard to do it with, you get the idea. So you'll see that. Okay, so it's a gained up version in voltage of the input. This would be in an ideal case. Okay, now the problem is the amplifier also has some noise. So what will that look like in your scope if your amplifier has some noise? Let's say green represents the noise you'll see in noise, so a low noise type of amplifier. What you'll see on your screen is you'll see your signal, but you'll see this kind of uncertainty around the signal. You'll see this, it doesn't look like a sharp line. So there's a voltage. So let's say if this was supposed to be, let's say this was supposed to be 1 volt at that peak, that particular peak, okay? Sometimes what this means is sometimes you'll see 1.01 volt, and sometimes you'll see, I don't know, 0.99 volts. Okay, there's this uncertainty. If you keep coming back to this signal, you'll see this very small variation. Okay, so it's just like the phone call from your friend. It's kind of screwing up the information. That's called the noise of your amplifier. Okay, now doesn't seem so bad, but you know, your amplifier might have a lot of noise. So let's say we talk about a high noise case. Your noise of your amplifier might look like this mess. Okay, now the amount of, so this would be like almost like noise equal to your signal at the output of the amplifier. Okay, so that ends up being a high noise system. So that's, you know, the definition of signal is whatever you're trying to transmit. Noise is what's screwing up that signal. And the reason it was originally called noise is, yeah, that's actually audio recordings. It's kind of like that hum thing you hear when you have listening to a recording or back in the day, televisions, you kind of see the snow in the background of, it doesn't look like absolutely sharp. It's harder to see that in sort of digital circuits now. So, okay, so now, so let's say, so this is you got an amp, you're recording it. You try to find an amplifier with low noise. Okay, fine. Now let's say you're trying to do recording a band. Okay, so let's say you've got one microphone and you got the vocals, and it's got its amplifier, so it's gaining up plus some noise level. Say noise, I'm going to call it noise level, noise 1, just it'll be some amount of noise. Okay. And say all these amps have the same amount of noise. Now you got the, I don't know, the guitar. Then another mic is picking up the drums. And another mic is picking up the bass. Oops, noise 4, let's say. Okay, so if any of you guys are into audio, don't make fun of me, because it's just like supposed to be a demonstration. So now let's say what you do is you overlay all these things to get the full recording, right? So you have some circuit, okay, that adds this with that. Okay, some circuit that lays this on top of that, and then you lay them all on top of each other, and then you take it to your recorder. Okay, so that's now I've got everybody playing together when you're recorded. That way you can adjust the individual channels. Maybe you reduce the gain on the drums or increase the gain on the vocals, etc. Now the problem is though that each one of these guys has its own noise that it's adding to the system. So the more processing stuff you do, you are adding more and more and more noise to your system. So this is an analog system. Okay, it's got signal. You're talking about voltage or current versus time or versus some other thing. Basically, your signal is typically voltage or current, and you're doing some kind of a processing to it, okay, directly. And the problem is, as you do more and more processing, you're injecting more and more noise into the system, okay? So what do? You buy expensive amps, expensive low noise amps. Are there any audiophiles in the audience? I tried to look into this about a year ago, and the price gets crazy. Yep.
Yes, sir.
Expensive.
Expensive. So you could spend, I don't know how much could you spend for a cable?
Oh, like hundreds.
Hundreds easily. Yeah.
It's a ripoff though, but yeah.
So, but that's what you got to do. You're sort of stuck there. And why is a cable expensive? Well, you got to get a lot of shielding in that cable. The connectors have got to really be good connectors to filter out don't let any noise come in. The amplifiers have got a lot of
gold plating.
What's that?
Gold plating contacts.
Yeah, gold plating. Yeah, I like that stuff. Yeah. Man, I bought some stuff from who are these guys? Bowers and Wilkins, which I don't think they're even at.
No, they're big. They're big. Bowers is good.
Oh man, but I got so pissed at those guys. I'll tell you a story later. It's just anyway. So if you're used to buying regular electronics, you're not going to want to play with analog hi-fi stuff, because you're in this situation where you're like debugging. You have to be like an electrical engineer debugging your system. And like, that's what they expect after you spend $5,000 on something. You're sitting there, well, did you use this cable, that cable? I'm like, dude, I'm used to plug in my, to a Bluetooth connection and working, but that's an analog system. Okay, so this is called an analog system, okay? And so for years and years and years and years, everything was done this way, okay? And why? Well, I'll talk about it, but if you remember, I talked about Moore's law. Okay, so Moore's law last time. And what Moore's law said was that the number of transistors in a silicon chip double every 18 months. Okay, so the way manufacturing works is the cost to the manufacturer is more or less the cost of the area of the chip, more or less. Okay, that means if you got this kind of exponential situation, okay, so like in 1970, back in the day, close to when the transistor was invented, the cost for a single transistor was, cost for one transistor was around $8, believe it or not. Okay, came in a can, used it, etc. But this exponential increase, we talked about billions and billions of transistors now in a chip. So the latest I could get data for was in, what was it? In 2010, I don't know. Cost for one transistor was, I have to make sure I get all this right. So it was 0.000000001. That's the cost for, because you're just putting more and more transistors. I got a billion transistor and something that costs $50. So the cost of each transistor is very little. Okay, so back when transistors were expensive, everything was analog. Okay, so this is what, and so, okay, so in comes digital. So we're going to study analog systems a lot because they're still an important part of electronics. I'll tell you why. So somebody used the example that your brain is actually, this thing that's stuck in a dark, wet place. It doesn't see anything. That could be a digital example of digital. The brain is not a digital thing, but you just think of it, the actual brain that we have has no eyes by itself, has no sensors, nothing. It just does processing. Okay, so that's the way you should think about a digital chip. Okay, now everything, so digital, and then, all our sensors are analog. We don't see, everything is, there's nothing, we don't see things in whether they're, that this thing is on, that thing is off. We hear a variation of stuff. So anything in the real world is analog. If you have a camera, it's analog. If you have, a microphone, it's analog. If you have an accelerometer for your cell phone to decide which way the cell phone's rotating, it's analog. Okay, so the whole world is analog. So you still need a lot of analog in all your systems. So again, to use the cell phone example, it has a camera, that's analog. You have a microphone, analog, accelerometer, analog, etc. So a digital system, what I wanted to say, it does not exist in the real world, right? So in comes digital. So a digital system is really a mathematical concept. Okay, so if we could do all our processing, do all signal processing, with just math, it'd be a zero noise system, right? If I say if I add 10 plus 6, it's always going to be 16. It's not going to be, some days it'll be 17, some days it'll be 15. No, it'll always be 16. Once you're in the mathematical domain, things are perfect. There is no noise on this, okay? No matter what I do here. So a digital system is really a mathematical space. So digital is just a mathematical way to process stuff, okay? And the beauty is that transistors, which is what we're really studying, are both, you can use them to create analog circuits, amplifiers, or transistors can also be used for digital math. Okay. So basically what we do is, and I'll talk about it, but basically those are the two things we'll study in the class. We're going to study transistors. On the way to transistors, we also have to study diodes. Diodes have some, you do use them in actual circuit design, but primarily they're a stepping stone to understanding transistors. And the two main uses of transistor are either to be amplifiers or filters, those kind of things in an analog environment, or used in a binaries or digital math as switches. Okay, so we'll talk about both of those. Okay, and sorry guys, somebody's calling me. Okay. All right. So, and why did it go from, so what the other thing is that doing this digital math is very, very transistor intensive. Okay. If I want to do this is, we're not going to study this in this class, but if I wanted to do a binary addition in 16 bits, okay, let's say in your audio circuit or whatever, you were going to do the same thing. You were going to add the bass and the guitar together using 16-bit resolution. So each bit needs 28 transistors per bit. Oops. And we have 16 bits. So, if you don't include anything else, this is, around 400 transistors. Okay, that's how many transistors you need to add two 16-bit numbers together in the digital domain, in the binary domain. Okay, binary is just digital with just two values, 0 and 1. Digital, you could potentially have multiple values, but almost every system, I think that you'll see all the chips, most of them are running in a binary 0s and 1s. Okay, but it's just a special case of digital. Okay, so back when transistors were $1 a piece, it was, it would seem insane to do anything digitally. You tried to do as little as you could digitally, because this thing would cost you, adding just two signals together would cost you $400. At $1 per transistor, you would need 400 transistors, plus physically these transistors were big. So, just adding two numbers might be the size of a shoebox and cost you $400. So going back to the 70s, 80s, even, early part of 90s, etc., you were still doing a lot of your processing with analog. So once the price of the transistor drops, though, you just do everything digitally, and you can just throw it as part of a much bigger chip, and you can do all your processing digitally. Okay, so for example, your cell phone, almost like all the stuff in your cell phone, almost all the stuff in your cell phone gets taken care of by one chip in your cell phone. It does all the audio codec stuff. It all does all the video processing for your camera. It drives the display. It, interfaces with all this stuff because it's just cheap. You keep throwing these very, very inexpensive transistors. You want a new function, just throw that in. So you do everything digitally because things have turned cheap now. So again, we're not going to do use the same example with recording the band these days. So as of 2021, this is how things kind of look. We use these things called analog to. We're not going to study these in this class. This is kind of what I do for a living. Analog to, or used to do this for a living. Analog converters. Okay. So basically what they do is they take a voltage in or current and spit out a, binary value out, like a 16-bit, 32-bit, depending on the analog digital converter you buy. So you basically, guitar, oops. So all these guys get digitized. I'm just making up symbols here. And I don't know. What is this guy? Drums. Okay. And so all these guys now go into a digital block, a digital circuit block. And some chip block. Okay. And this has like a jillion transistors, billions of transistors. It depends on what it's doing. Okay. And then these get added digitally now. Okay. So all this mathematical, all this digital math in this chip, it's all noiseless. So, there's still some noise from these analog to digital converters, but you just basically eat that up front, try to make those low noise, and all the work is going into those analog to digital converters, which coincidentally are full of amplifiers and all this stuff that we're going to study. And then after that, once you've got a 16, 32-bit, 8-bit, depending on your resolution of your ADC and your system, after that, all the computation is noiseless. So you can do not just overlay these things together, you can add all sorts of other recorded stuff, special effects, whatever you want to do, you can just add that stuff in there. And what's more, again, because this is usually a chip, it's already there, right? You're already going to pay for it. And let's say I also happen to have a camera, videotaping this recording. I can stick that into its own analog to digital converter, and that could also go in the chip. And I can link the video with my audio using the same digital chip. I don't know, if I had an accelerometer for some reason, I wanted to know how the camera was positioned so we could make sure the video was positioned correctly, I would just stick that into its own ADC, and stick that into the digital chip. Okay, so that's the concept of analog and digital circuitry. And we're going to study both in the class. And again, we're going to study them. You know, we don't have a lot of time. This is the first time you guys are seeing these microelectronic components and analysis techniques and so on. So we're going to skim through everything. It's still going to be, you know, a lot of work, difficult concepts, etc. But like, you won't be ready to design your own analog to digital converter by the end of this class. You just get familiar with a bunch of concepts. Okay, so that was my cheesy way of trying to explain to you guys the concept of analog versus digital circuitry. Okay, that's just sort of my opinions about what those things look like. Okay, so that'll keep coming up as you progress in your classes and when you go to work. It's analog versus digital concepts, signal versus noise. Why do you use digital or binary processing? Those kind of things. Okay, so now let's redraw this in terms of what we're going to study in this class. So if you're going to take the general topic of microelectronics, again, that's any time you put more than one transistor in a chip. Okay, so it's generally divided into analog and digital. These are both, so it'll have both concepts. Okay, so then we'll be studying a few different components. Okay, we'll have mentioned diode, bipolar transistor, and the MOS transistor. This is the stuff we'll be studying in this class. And all of them silicon, which is this material. Okay, so almost everything in the digital domain now uses MOS transistors. Okay, in the analog domain, we have a problem which makes our life a little bit difficult because you have discrete analog components. Okay, that's the stuff you might see in the lab. You'll get a part, stick it into your printed circuit board or use it, etc. That's called discrete. Or integrated, meaning that you can also put your analog circuit into the chip as well, on the same chip as all your digital stuff. That's called integrated. Okay, so the integrated stuff is almost all MOS transistors. The discrete stuff is almost all bipolar. Okay, why is that? Well, because the digital stuff is all MOS, so much research and development goes into MOS transistors, make them smaller, make them cheaper, make them, etc. It's like make them cheap, so we can cram as much of that craps on a chip. It's the same as the digital chip, okay? That if you're putting your analog stuff onto the same chip as your digital circuit, you want to use MOS transistors, okay? On the other hand, lots of stuff makes bipolar transistor do analog stuff better than MOS transistors. It's generally lower noise for the same amount of power consumption, lots of nice features. So if you were not forced to put your analog circuitry on the chip, you would probably end up using a bipolar discrete part. Okay, so what does it mean for our class? It puts us in a little bit of a pickle because I don't know which of you, or neither do you at this point, are going to go and do chip design and which of you are going to be doing sort of board level hardware design, okay, in your career, etc. So we're going to have to, if I knew all of you guys were going to do chip design, then I wouldn't even cover bipolar transistors in this class. I would just cover MOS transistors. and then vice versa. If nobody was going to do chip design, we do bipolar transistors. So we're going to be covering both. Okay, so basically we're going to be looking at digital MOS and analog bipolar transistors and analog MOS transistor circuits. And then another one, as I mentioned, there's this diode that's a stepping stone for us to learn about the other transistors and semiconductors in general, and is used in some very useful circuits. And then, so this is what we're going to cover. We're going to cover in this class silicon diodes, silicon bipolar transistor, and silicon MOS transistors. So this is almost all of microelectronics, in my opinion. Okay, there are other stuff, like if you go into, you see them in aerospace or power devices, etc. So I would call those exotics, which are a small part of microelectronics. So those are like gallium nitride transistors. I actually bought like a little power brick for my computer that was advertising gallium nitride transistors. They're good for sort of high voltage type of things and lower power. You might see gallium arsenide, et cetera. We're not going to be covering any of that in the class. Okay, guys, I somehow magically came very close to timing this right. So that was my attempt to give you guys an overall picture of what we're going to cover and why and what differences are between them. And anyway, if you feel like you didn't do great on the quiz, I suggest you take a good look at chapter 1 over the weekend, so you'll be ready to get moving with the rest of the class come Tuesday. Any questions?
Other than chapter 1, is there anything that we should go over just to prepare for Tuesday?
I'll also put up a little bit of a reading list again to skim. I'll put that up tomorrow, so you could read what we're actually going to cover on Tuesday. Anything else, guys?
I'm not sure if I missed this, but will you be posting these notes?
Yeah, what I do is I'm recording them and I put them on YouTube, and I put the link on Blackboard.
I mean, like, would you be willing to upload this as a PDF so I can notate it?
Oh, sure, I'm happy to do that. Yeah, I'll do that too. It's just I wasn't doing it last semester just because my handwriting sucks, but happy to do it if you'd like me to.
Yes, please.
Sure. Okay, guys. Any other questions? If not, have a good weekend and talk to you guys on Tuesday.
Thank you, Professor.
Thanks.
Thank you,
Professor.
Professor.
Good one.
Thank you.
Bye.